In this section, we're going to be looking at the basic shapes of graphs and talking about whether the graphs are increasing, decreasing, or constant. Before we do that, however, there are a couple first homework questions that are a little bit more relevant toward the last section that show up in this section as well, and that has to do with functional notation. F of x plus h means everywhere I see my variable I can plug in an x plus h. It does not mean that I can distribute the f to the x plus h or to the binomial following it. So f of x plus h does not mean to take the f and distribute it. It means everywhere I see a variable I'll plug in an x plus h. It also doesn't mean that I can distribute the f toward any part of this. So again, it doesn't mean to multiply and distribute. It does not mean I can go ahead and take this f and multiply it by the x and then add h or anything like that. So you're going to run into those types of homework problems at the very beginning of this section. I just want you to be ready for them. The types of homework problems that you will be running into are given graphs. We want to be able to talk about whether these graphs are increasing, decreasing, or constant. Now when we talk about whether they're increasing, decreasing, or constant, we're actually talking about the x values. So that's our first important point here. When we're talking increasing, decreasing, and constant, we're talking about x values only. So let's go ahead and take a look at the graph that we have here. And we can see parts of it look to be increasing, parts look to be decreasing, and another part here on the left looks to be constant. But let's go ahead and break this down and talk about the intervals. Now remember, we're only referring to x values, so only x values. Well, if we look at this part of the graph, we can see that at this point it makes this break. Something's happening here. So I'm going to put a hollow point there, and we'll see why in just a second why it's a hollow point. And then the graph is doing something here, and then it changes again. And again, I'm only interested in the x values. So at this point where x equals -2, something's going on, and then it goes off in this direction as well. So from here, reading the graph from left to right, this is called constant. So starting over here at -infinity and moving in this direction, at this point I have a constant graph. So when we're interested in talking about constant, then my graph is constant on the interval from -infinity, and of course we never bracket -infinity, all the way up to x equals -6. Now at -6 the graph is neither increasing nor decreasing. That's why we have a hollow point here, and that's why we'll always use parentheses when we're talking about constant increasing and decreasing. We never use brackets. And then from here down to this point where x equals -2, I can look at my graph and say, okay, well from here down it's decreasing. So the interval where my function is decreasing starts right after -6, so that's why I have a parenthesis here. At -6 it's neither increasing nor decreasing, and it goes off toward -2, and then at -2 I have a parenthesis because at this very point again it's neither increasing nor decreasing. And then I see here that it heads off toward +infinity in the y direction, and this is increasing. Now if you have problems with these, just think about driving your car. Here you're driving across South Dakota, it's very, very flat, constant, and then decreasing, and then we'll be increasing when we're going up a hill. So for my increasing portion, again, we're only talking about the x values. We would start at -2, because this is where it starts to increase, is when x equals -2, and then it goes off toward y values going toward infinity. But as y goes to infinity, my x values are going out further as well and going toward infinity. And again, we never bracket infinity. In fact, we don't ever use any brackets when we're talking about increasing, decreasing, or constant values. So this is going to be a typical graph that you would see. Yours might be a little less complicated or a little more complicated, but these are what we're looking for. Intervals where we're increasing, decreasing, and constant, we're talking about x values. Let's go ahead and review some basic shapes of graphs. Our most basic shape is just a line. So we could have a line with a positive slope. That might be something like y equals 3x plus 2. We could have something with a negative slope, and that might be something like y equals -3x plus 2. Positive slope, negative slope. Now if you notice, the only difference here is the 3 is positive and here the the 3 is negative. So these are linear graphs. We could also have quadratic functions. We could have a parabola opening up. We could have a parabola opening down. Then general shape of this graph is y equal positive x squared, and actually let's go ahead and call it something like 3x squared. Now here where the parabola is opening down, this might be something where the negative is out front from when we graph parabolas. And you can see with the leading coefficient being negative, it opens down. Positive leading coefficient, it opens up. We could also have some graphs that have a third degree polynomial. They might be something like this, or it could be something like this. It might not have as many terms, or it might just be a single term. This is something like y equals 3x cubed, and this one over here would be something like y equals negative 3x cubed. Now with the negative out front, basically we're starting up here and moving down into the negative direction. With the positive 3, we're starting down here and moving up toward positive infinity. You might also run across some square root graphs. So you might have a graph that looks something like this. It's constantly increasing but not very fast. This would be y equal positive square root of x. Or you could also have a graph that is underneath, kind of similar. It's getting lower and lower and lower, but very slow, and this is be y equal negative square root of x. Now notice the negative sign out front, the square root sign, it's not underneath the square root sign because that would produce a different graph. We could also have some absolute value graphs. This would be something like y equal the absolute value of x. We could also have something like y equal negative absolute value of x. Now notice it's upside down, negative out front, 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 going down, negative out front. So that's a common theme about the graphs that we're going to be looking at. Now there's other graphs as well, but for the most part we'll be focusing on some that are similar to these. Now another type of graph that we'll see in here, not just these individual graphs, but we'll be seeing piecewise function. So this example that we have here is straight from my math lab. It says evaluate the piecewise function at the given values of the independent variable. Okay, well you don't have to graph this if you don't want to, but it is pretty helpful. If you don't want to graph this, what we need to do is we need to look at the domain restrictions. So here we're looking at values that are less than 0. These are values for x less than 0. So that, for instance, would be f of negative 4 because negative 4 is less than 0. Now here we're looking at x values greater than or equal to 0. Well, the equal case is here, so f of 0 I could use here. And then I could also use f of 2. So I'd plug in negative 4 up here to find the value of negative 4. And I'd plug in 0 and 2 into the bottom part. Well, before we actually evaluate those, I would like to graph these just to kind of get an idea of what they look like. Now I'm going to be graphing these by hand, and then we'll also be graphing them with your calculator as well to double check our work. Now we're going to have a pretty fine point on this because this graph is pretty small. But what we want to do here is we want to look at values for x less than 0 and graph these points. So I'm going to go ahead and graph 0, even though it says less than 0, and put a hollow point there. So if I look at 0, 4 times 0 is 0, 0 plus 5 is 5, and that's a hollow point because I can't actually reach that value. Now next I can go ahead and plug in something like, maybe negative 2. So let's look at negative 2. 4 times negative 2 is negative 8. Negative 8 plus 5 is negative 3. So at negative 2 I go down negative 3. Now we can see that our slope is 4 over 1, so I could also look at this as rise 4, 1, 2, 3, 4, run 1. And again, rise 4, 1, 2, 3, 4, run 1. Now the important thing to remember, this is a hollow point because I actually never reached this value. Now the problem with doing these by hand is you have to be really accurate, and sometimes that's hard. So that's the 4x plus 5. Next we want to do the 2x plus 7, so let's go ahead and plug in a 0. So 0, 2 times 0 is 0, 0 plus 7 is 7. So this graph would start over here at 0 and then up 7. And I can fill in this point because I can actually plug in a 0 because I have an equal case here. Now my slope is 2, so I could do rise 2, run 1. And of course I kind of run out of graph here. It would look something like that. And of course my lines aren't exactly straight because I should have a straight edge. But this gives me an idea of what the graph kind of looks like. Now if I wanted to figure out what was going on at -4, then I could come over here and say, well, here's x equal -4, what is my y value? And I don't really trust this very much because it's not all that straight of a line, it's not all that accurate, but this is a general sketch. The next thing I want to do is I want to plot this with your calculator, and you can plot piecewise functions with your calculator. There's a couple of extra steps involved, but they are very doable. Okay, so let's remember what our problem was. 4x plus 5. Now those are only for values x less than 0. So let's go ahead and hit y equal, and we want to graph 4x plus 5. Now everything needs to be in parentheses because I want to be very clear about what values go with which domains. So I have 4x plus 5, and then in parentheses, this doesn't mean multiplication, this is my restriction. So this is where x is less than 0. Okay, now where are the less than signs? Well, if you hit under second test, here's my less than sign is number 5, less than 0. And then this is a plus sign, not to mean I'm adding things together, but that I'm adding an entire another piece of the function. So now I'll be adding 2x plus 7, which has to be in parentheses as well, close parentheses, and then I have to say x greater than or equal to 0. So that's under my second test. And then greater than or equal to is number 4, and that's 0, greater than or equal to 0. So let's go ahead and graph this and see what happens. Okay, there is my 4x plus 5, and then up here, this is my 2x plus 7 that kind of just runs off the page a little bit there. So I think I'm going to change my window just a bit. I kind of want to go up a little bit higher on my y max. So maybe I'll go up to 15 here, just so I can see a little bit more of the graph. And then we'll copy and paste this into our lecture, and then the next thing we'll do is we'll look at the table values. Okay, so let's go ahead and snip this into the lecture. So this is a piecewise function. And it looks a little bit nicer than my hand-drawn graph. Certainly the lines are straighter. Now if I wanted to evaluate like f of -4 and f of 0, I think I could do that here. Now one thing this graph doesn't show is my hollow and my filled points. Next thing I want to do is I want to go to my table on my calculator. So let's go second table. And our values went from at -4, 0, and 2. So we can see -4, 0, and 2 are represented here for my x values. And let's go ahead and paste those in as well. Okay, so we have a hand-drawn graph, and then we have a graph drawn by the calculator that's a lot more accurate, it looks like. However, this graph is missing a hollow point right here. This graph is not defined on this line at 0, it's defined up here, so that's my hollow point. Now, if I want to know what -4 is, I could go 1, 2, 3, 4 in the negative direction and move down, but it's still kind of hard to tell here. So I don't think this is going to be helpful, but this is helpful. This tells me right here that f of -4 equals -11. So this represents f of -4 equals -11. Okay, now next, f of 0. Well, I can look right on my table, and I see f of 0 equals 7. Okay, and then I can also see right over here at 2, f of 2 equals 11. So that's the table values. Now if you didn't want to rely on the table, or you wanted to do this by hand, you could as well. F of -4 is equal to 4 times -4 plus 5, because I'm plugging it in right up here. So 4 times -4 is -16 plus 5 is -11. Therefore, f of -4 is -11. And that just very much agrees with what the table has here. Now if I wanted to figure out what f of 0 was, I would take 0 and plug it into the second piece of my piecewise function. 2 times 0 plus 7. 2 times 0 is 0. 0 plus 7 is 7. Therefore, f of 0 equals 7. And then our last one, f of 2, and again that goes into the bottom one as well because of the domain restriction. So I have 2 times 2 plus 7. 2 times 2 is 4. 4 plus 7 is 11. So there we have f of 2 equals 11. So again, all of these values agree with the table and by hand. So it's a really nice way to go ahead and check your work to verify that your solutions are correct. Okay, let's go ahead and look at another example. We'll do this one by hand and with graphing as well. We're looking at a piecewise function and we're asked to evaluate it at particular points. Now this one doesn't have a less than or greater than. This one has an equal and a not equal to case. So to get started with this problem, let's go ahead and look at the restrictions. This piecewise function, I will use this upper piece for every single value of x except x cannot equal 4. Okay, so if we look at h of 3, well, 3 is not equal to 4, so that could be up here. So I could use h of 3 up here. And h of 0, 0 does not equal 4, so I could use that up here. Then I have h of 4. Well, that 4 does not equal 4. So O down here is where I need to go ahead and evaluate this h of 4. It doesn't fit this case up here, so it has to fit this case down here. Now notice this is just a constant, so this is just equal to 3. I know that one already. So let's go ahead and evaluate these by hand. I won't worry about graphing this one by hand because it's a pretty complicated function. It's a straight line with a hole in it, and we'll look at the graph here in a second. Let's look at h of 3. Again, 3 falls in this domain region, so 3 does not equal 4. So everywhere that I see an x in my original up here, I will go ahead and plug in a 3. 3 squared is 9. 9 minus 16, 3 minus 4 is negative 1. 9 minus 16 is a negative 7. Negative 7 over negative 1 is 7. So that tells me h of 3 equals 7. Now again, h of 0 would go with this upper domain restriction again because 0 does not equal 4. So everywhere I see an x, I'd go ahead and plug in a 0. So 0 squared is 0. 0 minus 16 is minus 16. 0 minus 4 is a negative 4. Negative divided by a negative is a positive. 16 divided by 4 is 4. Therefore, h of 0 equals 4. Now, h of 4 is a pretty straightforward one. It's kind of confusing, but it's straightforward once we see this. This says if we plug in x is 4, my y value is 3. There's really nothing to plug in there. So h of 4 is equal to 3. Now how would we graph this on your calculator? Let's go ahead and pull up your calculator. Go ahead and click y equal and clear out your last graph that you had in. Now we have to be really careful about how we use our parentheses here. I'm going to have one set of parentheses for the function, another for the numerator. So in the numerator we have x squared minus 16, close parenthesis, divided by x minus 4. Close parenthesis for the function, open parenthesis for the restriction. Now the restriction is x cannot equal 4. So x, and let's go to second test, and we're looking to the not equal case, so that's number 2, 4. X cannot equal 4. Now I have my close parenthesis. Now this is not adding the function in terms of combining them, but I'm just adding another function to the piecewise function. And then here I just have the value of 3, so that's pretty simple. Open parentheses for the restriction, and this is when x equals 4. So here's x, second test, equal sign is the first one, and we have 4. Now some of this is going to be hard to see on the graph because it's hard to see a single point on a graph, but let's have a look. So here's my x squared minus 16 over x minus 4. And then we can see when x is 4, 1, 2, 3, 4, we should be down here at 3, but this graph just has a tough time showing it because what your calculator does is it kind of plays dot to dot because it just doesn't know any better. So this graph is not really accurate, but we can fix it up so it looks better. And we'll look at the table as well. So this is a nice straight line, and you're probably surprised that this is a straight line because it doesn't seem like it should be, because you have that squared in there. But this has to do with restricting the domain and also with the cancellation and simplifying of the numerator and denominator. Okay, so what this graph really looks like. This says when x is 4, my y value is 3. So when x is 4, 1, 2, 3, 4, 1, 2, 3, 4, my y value is 3, 1, 2, 3. So that's a filled point. So that means straight above this on this graph should be a hollow point. So that's actually what this graph looks like. Now let's go ahead and look at our table values from our calculator to see if they match up here. So let's go to second table. I think we were looking at something like 0, 3, 4. Well, we can see when we plug a 0 in, we get a 4 back. If we plug a 3 in, we get a 7, but this is kind of where the trouble is, right here. Again, at a single point, the calculator has problems understanding what's going on here. So we're going to have to be smart enough to take the information that the calculator provides, combine it with the information that we know about the functions and the work that we did by hand to be able to actually talk about what's happening here with this graph. So h of 3. Here h of 3 is 7. We can see that that's here as well. So here we have h of 3 equals 7. And then h of 0 equal 4. That verifies this. H of 0 equal 4. And then there's that single point. H of 4 is 3. The calculator is confused. It says h of 4 is an error. We know it's 3, therefore h of 4 equals 3. So we can make that correction because we know how to read a piecewise function. Let's go ahead and look at another type of problem that we're going to be seeing, and it's going to refer to domain and range as well and ask us to identify a graph. Now there's several different ways that we can do this. Again, you can graph it on your calculator or you can graph it by hand. I recommend doing both just to make sure you don't have any errors in either one. This says the domain of the piecewise function is negative to positive infinity. If you notice here on the upper part, my domain is from x less than or equal to 0. Okay, that's negative infinity to 0, bracket the 0, parenthesis at the negative infinity. And then this piece says x greater than 0. So that means I'm going to start off right after 0 and go off toward infinity. I don't have an equal sign here, so I have to have a parenthesis. Now if you notice, because of that bracket in my upper domain, I have all real numbers covered here. Every single real number is covered. So that's why my domain is negative to positive infinity overall. Now it says to graph the function. Well, first of all, this piece, f of x equals negative 3x, that's basically a line with negative slope. Now f of x equal negative 3 is basically a line that's a constant. So I'm looking for a constant and a line with a negative slope. So if we look at this graph, it can't be right because this is a positive sloping line, and I do have a constant, but the positive sloping line, I throw that out. Over here, I have a constant and then a positive sloping line, so that can't be it. And over here, I have a negative sloping line and then constant, constant, and then a negative sloping line. So it could be C or D. However, this says for x less than 0, I should have my negative sloping line. So here's less than 0, here's my negative sloping line, so it's got to be letter C. Because over here, I should have a negative sloping line here when x is less than 0, and then my constant part of the graph should come up when x is positive, greater than 0. So C is definitely the correct graph here. Now it says, based on this correct graph, determine the function's range. Okay, so range is going to be a little trickier here. So my range, again, is my vertical up and down values. The lowest this graph ever gets is right here, let's say at, I plug a 0 in, looks like my y value would be at negative 3. So it looks like I'm at negative 3, and I'm actually touching that point of negative 3 right here, because then again I'm talking about my y values, not my x values. So I have a range of -3, but then I have this strange little gap, so we're going to have to figure out how to deal with that. And then it picks off again at 0 and heads off toward positive infinity. Okay, so let's see how this will look. Okay, so range -3. Now that's just a single point, so I'm going to go ahead and put this in our curly braces. And then I'm going to use a union symbol because this means -3 union with, and then I'm going to start off at 0 and head off toward positive infinity. And of course you never bracket infinity, but I can bracket the 0 because I have a filled point here. So this is the range, and this is how you'll put it in. The curly braces for the single point, union means include these values as well. Bracket the 0 because I start here and head off toward infinity. Now remember, we can graph these on your calculator as well to check your work if you want to check the graph. So let's go ahead and hit y equal and clear that out. Remember, we had in parentheses a -3x was my graph. My restriction was x less than or equal to 0, so I go x second test less than or equal to case is number 6, and that was 0. Close parenthesis, add another function. My other function is just good old -3, and the restriction for that is x greater than 0. So x second test greater than case is 3, 0. We'll graph that. And we can see pretty clearly here that it's not identical to what we have, but it's pretty close, and we'll see where the hollow points go here in just a second. Now when we paste this one in, we do need to add that hollow point because it looks like it's all filled here, but if you notice right here it doesn't quite touch the line. So that's your calculator's kind of way of saying, well, there's a hollow point there. It doesn't know how to give a hollow point, so the line just gets really close but doesn't quite equal that value. So our hollow point would be right here, and this would be an obviously filled point, and then they match up perfect, and the reason we need a filled and a hollow point is because of the domain restrictions in the original problem. Now the next problem we're going to look at is similar to the one we just did in terms of it's a piecewise function, and we're looking at the graph and we want to talk about the domain and the range, but it's a very, very different shape. So they tell us that the domain is all real numbers from negative to positive infinity again, and we can see that that's here x less than or equal to, less than 3 and x greater than or equal to 3. This is a parabola that's opening up, and it may just be a part of the parabola depending on how much is restricted here. Now this is just a line, and it's a line with a +4 for my slope, so it's a line with a positive slope. So if we look at this particular graph, parabola opening up, positive sloping line, that could work. Over here we have a negative sloping line and a parabola opening up, but it can't be this one because of that negative sloping line. Here we have a parabola opening down and a negative sloping line, so that's kind of a double whammy. And then here we have a positive sloping line, which could work for what we need from here, but then we have a negative parabola opening down, so it can't be this one. So I think it's A just by the process of elimination, but let's go ahead and see why. This says I have a parabola opening up for values that are less than x less than 3. So if we count here, 2, 4, 6, 8, 10, each of these tick marks is worth 2, so 3 would be right here. And if you plug in a 3, there's a hollow point, and then I have a parabola to the left, so this makes sense. And then at 3, I should have a filled point. 4 times 3 is 12. 12 minus 6 is 6, so here's 3, 6, and then I have that positive sloping line opening up. So this is our correct graph, part A, and you can kind of logic your way through that. You can also graph this. So to graph this, you'd go y equal, make sure you clear that out. We have 1/2 x squared, so that would be 1 divided by 2 x squared. Now our restriction here, remember we put our restriction immediately in parentheses, is x less than 3, and that's second test. Less than case is 5, 3, plus the other piece of my piecewise function was 4x minus 6, and of course that will be in parentheses, close parenthesis. Then I have x greater than or equal to 3. So x, second test, greater than or equal to is case 4, 3, and then of course we can graph. Now hopefully we can see most of this graph, but we might have to adjust our viewing window. So there's that parabola opening up, then we have a jump, and then there's our positive sloping line. Well, let's fix this graph up just a little bit to include a hollow point for my parabola. And then we can also talk about the range. I think the range will be easier to see from this graph. And get it made a little bit smaller. Okay. So from this graph, over here it doesn't look like there's hardly a gap. But from this graph we can see that there is. So there's a hollow point here, and then I have a filled point. Now if we want to talk about the range, remember our range is vertical values. So I'm looking at these values vertically. I can see that my vertical values start at 0, and then they head all the way up to here, and then I have this gap. So over here on my line I really should have a little bit of a hole right here. And at the top of this I have this hollow point. So this hollow point I could find by plugging in 3 into 1/2 x squared. So 3 squared is 9, half of 9 would be 9/2. So I think this is going from 0 up to 9/2. Now I can get that by plugging back into our original. 9/2 is 4.5. So this is 2, 4, and you can see that it's maybe a half in there. It's hard to estimate. That's why you'd want to go back up here to plug directly in for 3 to get an idea where this hollow point is. Now that's a parenthesis because I actually never reached that point, and then I have a gap. So I'm going to union this with my next value, which will be a bracket because I have a filled point, and you can see the filled point here as well. And that filled point would be if I plugged a 3 in. 4 times 3 is 12. 12 minus 6 is 6. And then this heads off toward infinity, which would be parentheses because you never bracket infinity. So these are some examples of talking about the domain and the range of piecewise functions. Now another thing that we can talk about is symmetry. So when we start to talk about symmetry, we basically are referring to whether a function is even or odd. So let's go ahead and start with an even function. An even function is basically symmetric with respect to the y-axis, the vertical axis. So the even function we want to remember is symmetrical with respect to the y-axis, so even y. So an example of this would be something that's symmetric with respect to the y-axis would just be a nice parabola opening up. Now it's symmetric with respect to the y-axis because we can see that any point on the right reflects to the same point on the left. Now we could also have, let's say, a parabola opening up that didn't start at the origin that's also symmetric. Any point on the right has an equal point on the left across the y-axis. So that's another example of a symmetric graph. So this is symmetric, and we use the letters WRT to represent with respect to the y-axis. So this is called an even function because it's symmetric with respect to the y-axis. Now our other type of symmetry is called origin symmetry, or it's an odd function. Now when we talk about an odd function or an even function, we're not referring to the power of the function, meaning, oh, the highest power is 2, therefore it's an even function. That could be, but then again it could not be. It just kind of depends on where this particular graph lies. Now an odd function is symmetric with respect to the origin. And this is a little bit different. So odd and origin, that's how I remember those. They both start with an O. So odd function is symmetric with respect to the origin. So odd function, it's symmetric with respect to the origin. So odd and origin. Now when we're talking about with respect to the origin, we're actually talking about with respect to the y equal x line. So let's go ahead and look at a graph, and this is a nice third degree polynomial, and the fact that it's third degree doesn't mean that 3 is odd, therefore this is odd. What this is referring to is this y equal x line. It bisects the first and the third quadrant. So this is the y equal x line. This is kind of that symmetric with respect to the origin line. Now if you notice, every point here is reflected across over here. So again, every point here is reflected across over here through the origin. And so this is called an odd function. So this is symmetric. WRT means with respect to the origin. And because it's symmetric with respect to the origin, this is called an odd function. Now, not every function is even or odd. There's also the case of neither. So a lot of times in a problem you be asked to find, is this function even, is it odd, or is it neither? So let's go ahead and look at a few graphs and try and determine those. So for all of these graphs that we're looking at here, and we're given the graph and the function that is associated with it, we want to talk about whether it's an even function, an odd function, or neither. Well, we can see that this one is symmetric with respect to the y-axis. Every point to the right is also to the left, has that exact symmetry. So symmetry with respect to the y-axis. Let's go up and look and see what that one is. Remember, odd was origin. Symmetric with respect to the y-axis, this is an even function then. So this is an even function. Now here, this would be symmetric with respect to the y-axis if it was moved over 1 unit. But as you can see right now, this doesn't split it exactly down the middle. So this is not symmetric with respect to the y-axis. It's not symmetric with respect to the origin at all. It doesn't flip on either side. So this one we would say is neither even nor odd. Okay, let's go ahead and look at this third graph. Now if we look right down the middle, we can see that there's definitely something going on with this graph, but it's not showing that it's symmetric with respect to the y-axis, because I don't have these 2 points on the left showing up as 2 points on the right. So it's not symmetric with respect to the y-axis. So I know right away that this is not even, because it doesn't have symmetry with respect to the y-axis. Let's try the origin now. Now there's algebraic ways to determine whether a function is even or odd. We're just kind of eyeballing them at this point. So I definitely see some symmetry. This point down here reflects up here. The origin point, of course, goes right through y equal x, so that makes sense. This point and this point reflect across this y equal x line. So this is symmetrical with respect to the origin. So this function is odd because it has this symmetric line right here through the origin, and it's symmetric or reflective across that line. Let's go ahead and look at graph 4. For graph 4, as we run down the y-axis, we can see that this point here doesn't reflect to that same point. So this one is not even. Well, let's see if it's odd. And it definitely doesn't look like it reflects on either side of the y equal x line. So this one is neither. Okay, let's run down y equal x. You can see a point over here doesn't reflect over here, so this one is not even. However, this one with the y equal x line, it bisects those quadrants, you can see that this point reflects to here, this point here reflects to this point reflects to this point. So because I have a reflection across the origin, this is called an odd function. Okay, and the next one, here's my y equal x line, or sorry, not my y equal x line, but my y-axis. And we can see a point to the left of the y-axis reflects to a point to the right, all the way through. So this is symmetric with respect to the y-axis, so this is called an even function. So it's pretty easy to go through and eyeball these. The odd function is probably the most difficult, but if you sketch in those axes of symmetry, whether it's the origin or the y-axis, it makes it a lot easier. The last part of this assignment, we're going to be looking at a graph, and with this graph we're going to be determining intervals of increasing, decreasing, and constant, and then we'll also talk about relative extrema. Okay, so let's go ahead and first of all get the correct graph in here. So here, it wants us to graph this on our calculators first, and it gives us a specific viewing window. So it says graph f of x equals 2x cubed plus 3x squared minus 36x plus 2, and this is the viewing window that they're wanting us to look at. So let's go ahead and do that first. So So we can hit y equal and make sure we clear what we have in there. We have 2x cubed plus 3x squared minus 36x plus 2. Now they want us to go to the viewing window, and they want us to change our window to -5 to 5. So we go -5 to 5. And then the 1 just means by 1 unit, and that's this number 1. And then it wants us to change our y min to -100 to 100. But instead of going by units of 1, they want each tick mark to represent 10. And then we go ahead and hit graph. Again, those are just the values that they provided. We could also choose different values, but this gives us a nice look at the graph, and it's all spread out. It's not crushed into one small viewing area because of that change in the tick marks. So let's go ahead and look at this graph and try and determine the things that they wanted us to from this graph. This is a little bit larger than the one that they gave us. Okay, so it says use the graph to find any values at which f has a relative max, and use the equation to calculate the relative max for each value. So we can see from right here the relative maximum point. This is relatively larger than any point around it, so this is called a relative max. Now this point is called a relative min because relative to all other points around it, this is called a relative minimum point because it's smaller than the rest of the points around it. So it says relative max and min. So for our relative max, we can see that this is occurring at x equal -3, and our relative min is occurring at x equal 2. Well, if they want us to find the value, the relative maximum for each value, they basically want us to plug -2 in, or sorry, -3 into my graph. So f of -3, I'd have 2 times -3 quantity cubed plus 3 times -3 quantity squared minus 36 times -3 plus 2. And now that's for my relative max. Now when you crunch those numbers, you can find that value, or you can also go to your calculator and go to second table. And these table values, remember, they were at -3 and 2. So here's -3 and here's 2. We can pull them right off the table as well. Now you can also see what's going on with the points around this. So I think this is pretty informative. So with this table, we can see at -3 I go clear up to 83, and if you notice it's higher than 66 and 70, so that's showing my relative max. So this is my relative max because it's higher than any points around it at 83. And then over here at 2, let's see if we can catch this one. This goes clear down to -42. So this is really low. This is my relative min. So this is the ordered pair 2, -42. And up here, this is the ordered pair -3, 83. So up here we have -3, and we get 83 out of this if you want to check it. And then for my relative min, I would go ahead and take this and plug it in to my original. Everywhere that I see an X, I'm plugging in a 2. Now from my table of values, I can get a -42, or you can crunch these numbers and see those as well. So what they want us to do here, I'll go ahead and pull in the exact question because they do have it worded a little strange. It says for the function f, it has a relative max or min. Let's go ahead and pop it right in here. So here we're looking at a relative maximum. So that's this value right here. Has a relative maximum, and the relative maximum is or are, and they want us to plug in these values. Now the first value that they're looking for is x. So the relative max was at x equal -3. And then our y value would be an 83. So just to be specific, I should be more careful here, they're not looking for x equal, they just want the value at x, which in this case was -3. So here they want -3, and the value was equal to 83. So you don't have to put in x equal and y equal, they just want the x value, and the maximum value is 83 when x equal -3, and then you'll do the same thing for a min. So if you have questions about the lecture, please bring those to class, or you can stop by the Math Center as well. We're happy to help you out. This homework isn't too bad. Just make sure you read through the instructions carefully. Good luck on this assignment.